In this example we have a two-bar linkage, but instead of the link between the two bars being fixed within a bar, it's at point P, and so it's fixed in bar B, but then it can slide along bar A. And our task is to find out what the inertial velocity of this link between the two bars, point P, is. We're going to do this two different ways. The first way is when the linkage is in this configuration and has an angular velocity input of omega A. And then the second way that we're going to analyze this is to develop a general expression which is going to be true for any configuration of bar A and bar B. But before we go on, we need to apply reference frames to the problem. First, we have our inertial reference frame. Its origin is at O. E1 is defined along O prime, E3 out of the plane, and then E2 as the cross product of E3 and E1. The reference frame A, which is a body frame on bar A, has an origin of O, A1 along OP, A3 the same as E3, and then A2 the cross product of A3 and A1. And its angular velocity, as observed in the inertial reference frame, is omega A in the A3 direction. And finally, a reference frame attached to bar B. This frame has an origin at O prime. B2 is in the O prime P direction. B3 the same as E3, and then B1 is the cross product of B2 with B3. And the angular velocity of the body frame B, as observed in the inertial reference frame, is omega B along B3. Finally, let's add our transformation tables. And here we see that we're relating the A frame to the inertial reference frame through an angle theta, which is counterclockwise. And for the B frame, we're relating the B frame to the inertial reference frame through a counterclockwise angle phi. Now in this problem, we're interested in the velocity of point P as well as the angular speed of this bar B. And so the strategy that we're going to use is to find the velocity of point P with respect to point O, an inertially fixed point, and set that equal to the velocity of point P with respect to O prime, which is also an inertially fixed point. And so if we're making those observations from an inertially fixed point, they should be equal with each other. So for the velocity of P with respect to point O, as observed in the inertial reference frame, we're working through bar A. So this is equivalent to the time derivative, as observed in the inertial reference frame, of our position vector Rp with respect to O. And because we're working through bar A, we'll apply our transport theorem, which is the time derivative as observed in the reference frame A of that vector, Rp with respect to O, plus the angular velocity as observed in the inertial reference frame crossed with Rp with respect to O. And so for this term in which we have the time derivative as observed in the A reference frame, if you're on this reference frame A and then you're observing point P, then the time derivative of this is only going to be in the A1 direction. So we write this as the speed of point P, it's a scalar, along the A1 direction, because it can't be in the A2 direction. And remember that A1 is always going to be along OP, and so it's going to be rotating, and it's a non-inertial reference frame. And so we fill in the rest of the expression, which is plus omega A, and that's in the A3 direction, and then we're crossing that with Rp in the A1 direction. So let's add that dimension, in which we have the distance R sub P, which is the distance from point O to point P along the A1 direction. Now I mentioned a moment ago that we're going to be taking our velocity of point P with respect to O and our velocity of point P with respect to O prime and setting them equal to each other. Now you can see here that our velocity of P with respect to point O is given to us in a basis A1, and then A3 cross A1 is going to be A2, So it's in our basis that's fixed to the A frame. Now we're going to set that equal to the velocity of p with respect to O prime. And when we do that, we're going to be working on bar B, and so that's not going to be in the A basis. It's going to be in the B basis. And what we've done in our transformation tables is we've related our A basis to our inertial basis and our B basis to our inertial basis. So at this point, as we're thinking ahead, let's change our A basis to the inertial basis, and we'll do the same thing from our B basis to our inertial basis in a moment so we can equate these two together. And so if we make that transformation right at this step, we see that the A1 vector is decomposed into a cosine theta E1 as well as a sine theta E2. Our E3, or our A3 is the same as E3, and then this RP in the A1 direction, we can rewrite that as a horizontal distance plus a vertical distance because of the configuration in which we're using this. And so our horizontal distance, we're calling this D, so here's our D, and then our vertical dimension would be 0.4. And so that's the dimension from O prime to P. We'll collect our terms, and then we'll set that aside until we finish the velocity through bar B. So now we calculate the velocity of P with respect to O prime as observed in the inertial reference frame. And so applying the transport equation, it's the time derivative as observed in the B frame, and this will be of the position vector of P with respect to O prime, and then plus the angular velocity of frame B as observed in the inertial reference frame crossed with the position vector of P with respect to O prime. Now this expression ends up being the same thing that we've done prior to learning the transport equation because the time derivative of this position vector as observed in the B frame is equal to 0. It's actually fixed in the B frame. So we insert our angular velocity, which is omega b, in the B3 direction, and then we're crossing that with the measurement h in the B2 direction, and from this we're going to get negative h omega b in the B1 direction. And in this position, B1, if we convert to our inertial basis, B1 is the same as E1, so it's negative h omega b in the E1 direction. We'll take our two expressions, so the velocity of P with respect to O as observed in the inertial reference frame, and the velocity of P with respect to O prime observed in the inertial reference frame. You can see that we have these expressed already in the inertial basis, so we can just set those two equal to each other. And when we do that, we get two scalar equations, and we're looking for two unknowns in this case. The speed of P, and that's with respect to O, and then we're also looking for omega b, so the angular speed of bar B. We can solve for these and get two different expressions, and that's the speed of P is equal to negative d omega a divided by sine theta, and then the angular speed of bar B is equal to the angular speed of bar A multiplied times d over h cosine theta sine theta plus 1. Now it's really important to point out that these two expressions are only valid in this configuration that we see right here, which has a horizontal distance of 0.3 and then a vertical distance of 0.4 to point P. Because we've already made those assumptions, because we've lined up our inertial reference frame with our body reference frames. Remember, we said that E1 is the same direction as B1, and we've said that E2 is in the same direction as B2. And so in other words, phi is equal to 0. So now let's substitute in our unknowns. or rather the dimensions that were given to us in the problem. We're given these in the problem, in which the horizontal distance from O to O prime is 0.3, the vertical distance from O prime to point P is 0.4 meters, our angular speed is 2 radians per second, counterclockwise, so that's positive. And then we can see by the triangle it's a 0.3, 0.4, 0.5 triangle, so cosine theta is 0.6, and then sine theta is 0.8. And when we make those substitutions, we find that the speed of P is equal to negative 0.75 meters per second. Remember, this is only in the A1 direction. Our angular speed of bar B is equal to 3.125 radians per second. So that means it's rotating counterclockwise, which is intuitive given how the system looks. And then the inertial velocity of point P is equal to negative 1.25, and it's in the E1 direction, so 1.25 in the negative E1 direction meters per second. And so to recap, what we have here is that we've been given this problem in which we have two bars and then we have a sliding connection between the two bars. And we were given this problem in this configuration, and we were also given an angular speed omega a. And so told to find the instantaneous inertial speed of point P as well as the instantaneous angular speed of bar B. And when doing this, our strategy was to find the inertial velocity of point P as observed, or using bar A and then using bar B, setting those equal to each other, and we got enough equations to work through this. Now, as we work through this, let's point out that we used our transformation tables to put our answers in a basis that was the same so we could equate the equations. And then from that, just plugging back in what we knew, we're able to get the inertial speed P, the inertial velocity P, and then the angular speed of bar B.